Hello everyone, the title of this paper is GaussianMask, Uncertainty-Aware Instance Segmentation based on Gaussian modeling. My name is Seungil Lee and I'm from Seoul National University of Science and Technology. Now I started. Here's the content in this paper. In the introduction, I'll explain the motivation behind the research. And then in the background, I'll talk about the calibration problem in deep learning and different methods for estimating uncertainty to address this problem. After that, I'll summarize our contributions and then discuss the experiments and conclusions. First is problem definition. Recently, deep learning is overconfident and it is difficult to trust detection result. So applications that require reliability are difficult to apply and studies are being conducted to resolve this. However, these studies have high complexity, such as obtaining mean and variance through multiple forward passes, like Monte Carlo dropout, and it is difficult to obtain uncertainty while minimizing processing speed. And then, how can we improve the segmentation accuracy with negligible increase in computations? Next, backgrounds. First, let's talk about calibration in neural networks. The recent models are overconfident in their own predictions, so their confidence scores don't fully match real accuracy. The paper shows this with LUNET and ResNet examples. More recent models like ResNet are way overconfident, with most predictions here near 100%. So the gap between confidence and actual performance, called error, is high value on ResNet. Next, I'll go some ways to researchers try to estimate uncertainty to tackle these issues. A standard deep learning used fixed weights, but Bayesian deep learning makes them stochastic, such as average and variance instead. This can improve performance, but models get huge because you have to represent so many weights. A basic way to measure uncertainty is Monte Carlo dropout. It uses dropout layers during inference. As the figure right side shows, running the same model multiple times here with dropout gives slightly different outputs each run. We can use the variance across those outputs as measure of model uncertainty. This successfully extracts uncertainty, but very slows down inference time. To avoid that problem, Gaussian YOLO V3 efficiently predicts uncertainty using Gaussian modeling. They adjust the number of channels in prediction heads to output uncertainty. My method expands on their method for instance segmentation. Next, the method we propose. There are lots of ways to estimate uncertainty, but we use Gaussian modeling. It's very simple, so I base my approach on YOLECT, but it works for other segmentation networks too. First, we model heads after the backbone, as the left figure shows. One head predicts the mean, and we add a new head of the same size to predict variance. Then, in YOLECT, the outputs combine with the protonet. The uncertainty map looks similar to other methods. In our Gaussian mask, we model the mask head as Gaussian with mean and variance values. Usually, segmentation's ground truth is binary value, so object or not. So loss function follow a Bernoulli distribution. But that means each pixel scores corresponds to just one fixed value, as the solid green line shows for mask RCNN and YOLECT. Different score values don't change variance, so we can't easily distinguish between correct or incorrect detections. So we model the predict mask as Gaussian and optimize with NRL loss, so pixels get unique mean and variance values. With the same scores, pixels not have different uncertainties, as the figure shows. And we can use uncertainty for better post-processing. First, post-processing method. In instance segmentation, confidence scores don't reflect mask quality. Like the right side figure, mask can be incomplete but still get high confidence, shows in 0.61% confidence scores. Mask scoring RCNN introduced mask IOU to rescore mask, but that took more layers, costing computation. Our Gaussian uncertainty predicts quality without extra layers and correlates strongly with mask IOU as shown in the left side. So we penalize confidence with uncertainty to balance them. This rescores each object, weighting by size using gamma, here gamma. And since uncertainty tends to be higher near boundaries, the denominator counts non-zero pixels, the numerator sums uncertainty. Small objects get weighted more as incorrect pixels impact them more. This balance confidence score and real mask quality. Next, we use uncertainty to make each pixel more robust. The figure shows what pixels were predicted as, and generally, first positive and first negative have higher uncertainty than true positive or true negatives. And incorrect pixels cluster around 0.5 confidence. So we reward confident true predictions and penalize unconfident false predictions using these equations. If uncertainty is higher than a threshold, we penalize the prediction by that amount multiplied by alpha, set experimentally to 0.3 in this paper. Lambda is 1 or -1 based on the 0.5 threshold. Next, experimental result. First, visualize sample. From left, we have the original Yolect output and uncertainty map and result after processing. The green box shows incorrect original masking, and despite that, the blue box has 100% max confidence. The uncertainty map clearly highlights the bad pixels. So first, our method rescores object with total uncertainty to balance confidence and quality, visible in the blue box score change. And then we clean up errors pixel by pixel, removing first positive on the food and hair in the green box. Our approach improves segmentation accuracy. Now, performance compared to other method on Coco dataset. We applied our technique to mask RCNN and YOLECT. For YOLECT, we get a 2.1% MAP boost over baseline. For mask RCNN, it's 1.8%. And as the blue box shows here, computation only increased slightly, 8.6 to 8.2 for mask RCNN, and 33.5 to 32.5 for your left. Below visual results also showcase improvement. Next is video evaluation. See how our method result in more solid post-roof masking. Here. Next is conclusion. In conclusion, we successfully improve in sun segmentation accuracy with minimal computation cost. Gaussian modeling extract uncertainty for post-processing. First, we rescore mask to balance confidence score and quality. And then we leverage pixel level uncertainty for cleaning up errors within predicted mask. We expect promising semi-supervised performance as well. Thank you for listening my presentation.